I'm going to do something a bit different today. I'm going to ask you guys to look at my results first. So I've got two pictures here. One of them is a actual physical scan of an industrial part, and the second one is entirely simulation. So see if we can have a look at a bit difference. I do want to point out these images are not registered, so there's a slight offset with the tilt, and the material properties, although they are within standard, they're not exactly the same. So if you take a look at a line profile through the center line, this is going through the little hole here. You can see the noise is the same. The noise is actually the same standard deviation on both images with a 0.003, and there's the little material discrepancy here. If you pay attention to the top edges, the blur you get is the same, and these images are quite close. I'll give you a hint. One of these is a CAD model. The actual simulation is B, and you can kind of see, I don't know how easy to see on these projectors, the screws are too perfect, whereas on A we have some filled cavities. The interesting part is that we found out that the manufactured part is slightly out of spec because we're having some larger edges here compared to the backplane. And yeah, so I'm going to now jump back to my title and explain what it actually is. So I'm talking about creating digital shadows of X-ray systems. We've all heard today people mentioning digital twins, and then digital twins, as we know, are virtual representations of physical objects or processes, but they are continually refined using collected data over time or in real time. They're an active model which stays up to date with their physical twin. Digital shadows are just a snapshot of a system in time. So what I've been doing is actually using experimental procedures to characterize existing X-ray setups. And if you took multiple characterizations over time, you'll have a digital twin, but alas, these are just models. But with the combination of X-ray simulation, which is becoming quite more popular, I've seen it being used multiple times as conference, and CT is also quite prominent at this conference. We can actually transform these characterizations into functional virtual systems. And this opens the door to representative X-ray simulations, where you're not just scanning your sample on a perfect setup, you're scanning on your sample on your machine you may have nearby locally, or in a specific machine in a beamline. So, X-ray simulation, virtual scanning, I get to explain all this all over again from Frank talks yesterday. It's increasing in popularity with this push towards data-driven models, machine learning, component testing, digital twinning. And the thing is, what simulated results can do, if they're calibrated properly, is actually answer feasibility questions without requiring beam time. I had a good talk before about doing a parameter sweep to find the best settings to X-ray your sample, and that probably cost a lot of time to take all those scans, and that can probably be used better elsewhere. The thing is, you can also use calibrated simulations for quantitative analysis. You can compare your simulated sample and a real scan much more accurately. And we're mostly using G-virtual X-ray, which is really fast and also very accurate compared to the slower Monte Carlo particle-based simulations. So I got the great opportunity to go into Lyon 2 months ago, well actually 3 months ago, July, and we managed to make a digital shadow of their DTHE system. This is a dual source, dual detector system, which just sort of crossed. As we were there, one of the sources broke, so we only got to characterize half the system. And we were working to make a digital twin. So I get to explain X-ray CT again, like everyone else has done this conference. Everyone knows at this point you've got your detector and your source, and then your sample goes into the middle. For characterizing the system, this is nice because we only have the two components to deal with, the detector and the source. I'm going to start with the X-ray detector. X-ray detector converts X-rays into electric signals. It's a fancy camera. Most common form is these flat panel detectors, which use a scintillating crystal layer, which absorb X-rays and re-emit visible light, which you then capture using standard optics. Standard optics are standard. They have a sort of noise, electrical noise. This is a fixed pattern noise from the detector you can see above, where you can actually see the construction of the detector. Thankfully, this is sort of a solved issue. We normally do flat field correction, where you take an image of your noise and then you're able to convert that into a white image. For our characteristics point of view, we don't have to therefore model exactly how all your pixels react if we're functioning on flat images. A key point, however, is the point spread function. Because they use a contrast is quite bad, but they use a scintillating layer. There's normally a divider between each sort of crystal ahead of the photons to keep electrons contained, but you do end up with stray electrons from the interaction, which depends on your power. This gives you a sort of spread. So if your X-ray hits one point, it'll trigger a pixel next to it, and this results in a blur for your image. So you can measure this experimentally by taking a sharp edge and doing an edge response function, and then taking a gradient which gives you a line spread function. If you want to convert this to a point spread function, which is a 2D version, you have to measure in both horizontal and vertical axes. The thing is, LSF, I don't see many people talking about it, but it does play a huge part in image quality, where if you take your perfect detector response, you get these crisp images where you're able to see the individual pixels. And if you use a real LSF, it just turns into a blur. So we swap between these. And yeah, most people think this may be your focal spot, but this is in addition to your focal spot. So the detectors, leave it there for now, and we'll jump back to the source. There are other parts of the detector, such as the scintillator material and thickness, but manufacturers don't like talking about that for some reason. So creating the X-ray source model is a bit more involved. X-rays sources, in this case, are the standard tube sources, which take an electron beam and hit a tungsten target. This tungsten target then emits X-rays. So X-ray tubes are polychromatic sources. They don't emit a specific energy. They emit a distribution of energy. And thankfully, this has mostly solved the problem. There's a lot of sources in literature, and you can get very characteristic curves. There are open source tools such as SpecPy and XspecGen, and these are Python libraries where you can import your tube voltage, your target, your angle, and they emit you these nice graphs. If you want to do filtration, the filtration acts on this graph, and so a copper filter would remove, say, all of the bottom frequencies, energies at the bottom, and give you a more focused higher band. What they don't give us, though, is the flux. We know the distribution of energy, but we don't know the amount. So photon flux is quite a hard issue. You need to know your entire system end to end to work out your flux, and this is not really possible. A lot of synchrotron beamlines know exactly their flux because they're able to measure it and they know all the components. But if you're using a lab or industrial scanner, you won't know exactly how your tube or detectors are constructed, so it's hard to measure. What we can do, though, is look at the noise. Noise is a proportion represented by the amount of photons you receive. And so if you know the noise in your system at different parameters, you're able to inversely work out the flux. We took over more than 700 scans at the DTHE, changing the voltage, amperage, exposure, distances, to end up with this nice photon count database. It's also the most boring X-ray images you'll ever see because it's just 700 pictures of like TV static, and there's nothing interesting in them. But by working out all this photon count, we can work out how our tube and target work, our tube works. And the first part we're going to look at is the amperage and exposure. Amperage and exposure should have a linear relationship. However, when we did our initial data analysis, we ended up with these graphs. So on the left-hand side, we have a change in amperage and a fixed exposure. And on the right-hand side, we have a fixed amperage and changing exposure. Both of these graphs should be linear. We have a nice linear graph for our detector, which is our exposure. However, when we expect a linear change in our amperage, we did not get one. So there's a bit of a discrepancy going on. We found out that the amperage you put into the tube is not the amperage of the target, as you can sort of, I have a guess about. However, this is quite a large discrepancy. So our tube we had could go up to like, I think 500 microamps. But if you put in that amount, you're only getting about like 300, 3,500 microamps. So at even some, you end up with a 60% difference. And if you want to have a linear situation where you're losing things, it's not the best. There's also some standard deviation issues, and while doing the sweep, because this changes depending on your voltage as well, we actually managed to find sort of the best case, which was around 100 keV. So we found out where the manufacturers are fine-tuning their tubes. So we got the flux. The last thing is working out the voltage on our flux, and with our fixed MES curves, we end up with these nice straight lines, and you can see the effect that the kilovolt into the tubes has on your photon count. You can actually work this back into a sort of nice curve of which we decided to fit using a third order polynomial, and it's the blue line you can see here. So as you increase your tube voltage, each kilovolt has an extra proportion to how many photons it makes. So we've worked out the effect of amperage on our noise, the effect of exposure on our noise, and the effect of voltage on our photon energy distribution and our photon flux. So the last thing we really need to do is distance, but then distance is quite easy because it's just the universe square law. We took 3 different experiments at different distances, and quite hard to see, but in the orange and green lines are actually dotted lines, and these are estimated flux over distance by using the first line. So it's quite hard to see, they're very close. This is just a quick and dirty. This doesn't actually take into account the attenuation of air, but the results we're getting are quite close, and the air attenuation has a very small effect at this point. So we're able to record accurate characteristics of X-ray systems from detector to source and model noise correctly, to the point where a user can change the voltage and amperage of a tube and end up with an X-ray image exactly like they'll get on a real setup. Using these characteristics, we can do representative simulations, which are identical to real scans. And the created digital shadows you can use for feasibility tests, you can use for expected results in industrial settings, use it for machine learning training sets, which are better targeted to equipment, and even lifecycle tracking if you decide to take these regularly and see how your effects compare to each other. The future work is, you may have noticed there's no little bit about focal spot size. I do have the data for that, it's just taken some time to process. We only did this about 2 months ago. There's some things to do with the detector construction, such as the scintillator. We don't actually have the measurements from the manufacturer, they've not told us, so we'll have to reverse engineer how their detector's working, which should be fun. And we're also planning on putting these models into GVXR, so you can just say, use system DTHE, enter your voltage and amperage, and then use this digital shadow for representative scan. And we've also proudly got data from NXCT's Nikon, which was used in the talk yesterday, so you'll be able to use that as a digital shadow too. And thank you for listening.